Good morning, afternoon, or evening. Today we want to talk about Chapter 4 in our statistics course, and that chapter is titled very simply Probability. Probability is necessary to understand what comes in the later chapters. Statistical decisions are based upon probability. Some people have said statistics is just applied probability theory. Well, we don't need a lot of probability, but we need a fair amount. And so I'm going to try to cut down Chapter 4 and give you just what we need for the rest of this course. So let's start thinking about probability as likelihood that something will happen or the relative frequency. And that's probably fairly close to your native or intuitive understanding of probability. We need to identify things like, can you tell if I put milk in your cup and then tea, or if I put tea in your cup and then milk? And this is a famous story. It involved a statistician whose name is R.A. Fisher and a nice lady that he was having tea with one afternoon, and she claimed that she could tell the difference if you put milk in her cup and then added the tea, or if you did it the other way around. And so in order to test this, he gave her 10 cups of tea with milk in one way or the other. Milk first and then tea, tea first then milk. She didn't know, but he did. So 10 cups of tea and milk, and do a count of the number that she correctly identified as tea first then milk, or milk first then tea. So in order to ascertain if her claim was creditable or not, we looked at the probability of the resulting number of correct outcomes. The resulting number of correct outcomes. And we could look that up. I don't remember how many she got, but she got a large number of them correct. And let's just suppose, now here I want to introduce the notation also. This P, capital P with the parentheses around it, the P stands for probability, the probability of, and then this is some event, some outcome of an experiment that's inside the parentheses. So if this probability was equal to 0.50, you'd say, well, she doesn't show much unusual ability here. Half the time, a person with no ability to distinguish would get this number of outcomes correct if the probability is 50%, because we're thinking about probability as the likelihood or the relative frequency. So if we did this a lot of times, people with no power would get about 50% correct. But let's just suppose that our nice gray-haired lady came up with an outcome that had a probability of occurring of say only 4% of the time, or 0.4 as a decimal. Well, that's pretty surprising. If the assumption is she has no ability to tell the difference between what went in first, tea or milk, then whenever we gave her 10 trials, she came up with a number correct, that would only happen 4 times out of 100 if she had no special powers. If a person is just guessing, her outcome would only happen 4 times out of 100. So do we find that likely? Well, this is how we do statistics. If we find that the result is not likely, then we're not going to say it's untrue. We're going to say, I doubt that. I don't think that is likely to be true. All right, so we're going to do more and more and more of that. There's going to be a lot of those kinds of logic problems that we'll be dealing with. In general, if the likelihood of an event is less than 0.05, we say that's unusual, or maybe we'd say it's a rare event, or we might say it's just unlikely. And this 0.5 is a bit arbitrary, but almost all statisticians routinely use 0.5 as where events get unlikely to have happened. Now, again, all of this is a foreshadowing of things to come, but events with probability less than 0.5 are generally deemed unlikely events. So let's scroll just a tad. There are 3 ways that we define probability. The first way is called the classical, and if we'll use uppercase letters like A, B, C, D, we'll generally use these for events. Events are things that we can observe happening. So if A is an event, and if A can happen N of A ways out of just say capital N possible outcomes, then we say the probability of A is N of A over N. And I'm trying to avoid going through 2 days of vocabulary here, and in the end that may prove to be a mistake because we need vocabulary to discuss things, but maybe we can accomplish the same thing through examples. And so let's just suppose that we've got a jar. This is my rendition of a jar. And inside it's got colored balls, and some of these are red. Okay, these are like marbles. And some are red, and some are blue. And what have I got here? Just count 1, 2, 3, 4. 4 red, and 1, 2, 3, 4, 5, 6, 6 blue. Then we want to let A equal the event. We draw red ball or marble or sphere. Now I need to think about then, to use the classical definition, I need to think about the number of ways that A could occur. Well, A could occur 4 ways. I could reach in and get this one, or I could reach in and get the second ball down here, or I could reach in and get this ball, or I could reach in and get that ball. So N of A would be 4. And then I need to think about the total number of things that could happen when I reach in and select a ball. And when I just reach in and select a ball, I could get any one of the 10, right? 4 plus 6. I could get any one of the 10. So there would be 10 outcomes that are possible, and 4 outcomes favor the event A. We'll call A an event now, or an outcome. So we would say the probability of A is equal to 4 over 10. And probabilities can be written as fractions, 4 over 10. Even better would be to reduce the fraction to lowest terms, and equally good would be to express the fraction as a decimal. You'll see rules in your book about how many digits to use for fractions, and so you can read those. I find that just habitually the number of digits I use depends upon the situation. Here, 0.4, if I wanted to use 3 decimal digits, it would be 0.4000, so that's the same as 0.4. Other times when we're calculating more complicated events, I usually use 4 digits for probability. I think Marty Triola is more apt to use 3 digits. That's just, I don't think, worth arguing about. So this would be the classical definition of probability. If we would toss 2 die, that is a pair of dice, right? What's the probability that the number of pips, those are the spots on the die, on top, is equal to 12? I can use the classical definition here and say that there's only one way, there's only one outcome, only one way to get a 12 when I roll a pair of die, and that is they've both got to be 6. And so there's one way to do that. And there would be 36 things that can happen when I roll a pair of die. I could get 1 through 6 on the first die, or a 1 through 6 on the second die. So altogether that gives me 36 outcomes. So the probability of getting a 12 when I roll a pair of die would be 1 over 36. That's classical. Now, in order to use the classical definition, we've got to have these different outcomes that we're counting to be equally likely. So as I roll 2 die, there is no preference of the die to come up one number or the other. These 36 outcomes that I could get whenever I roll the die would be equally likely outcomes. And when I reach in and select a ball or a marble from this urn, an urn is a jar, when I reach in and select, I'm mixing them up and I'm not looking, and so I'm as likely to get any one as any other one. These 10 outcomes are equally likely outcomes. These 36 outcomes are equally likely outcomes, and that's necessary if we're to use the classical definition of probability. Now, there are events, probability events, that we would be interested in that just don't fit that definition. And then we can use a second definition called empirical probability. And the classical illustration here would be, think about taking a thumbtack and tossing a thumbtack. And when I toss a thumbtack, it lands sometimes like this on its base, and it lands sometimes like this on its side. And those are the only two outcomes. If I toss a thumbtack, it's going to land one way or the other. But the question would be, first of all, are those equally likely? Is it as likely to land point up as it is point down? And just toss thumbtacks just a bit, and you'll soon discover that no, these aren't equally likely. It's more apt to land one way than the other way. I'm not going to tell you right now which way is which, but they're not equally likely. And so the classical definition of probability just doesn't work. I can't just say the probability that my thumbtack is going to land this way is equal to, that's 1 out of 2 possibilities. That would be using the classical approach, but the outcomes are not equally likely, so this is not valid, and I can't do this. But what I could do is to use the empirical probability definition. And so I would start to toss the tack a large number of times. And I would keep track of the number of times that the tack landed point up divided by the number of tosses. And that might fluctuate wildly at first. Like I might have, it could be 0 over 1 if I got a point down the first time. And then if I got a point up, the totals would be 1 out of 2. And then if I got a point up, it would be 2 out of 3. And then if I got a point down, it would be 2 out of 4. And then another point down would be 2 out of 5. And I want you to keep going like that. But eventually this ratio will settle down, and it'll get close to something. If you think about graphing this, 0 out of 1 would be 0, and 1, let's put 1/2 in here. 1 out of 2 would be 1/2, and so this would be the toss number, and 2/3 would be up here, and 2/4 would be back down here, and 2/5 would be over here. So I could graph by connecting the dots, and I'd be getting a graph that'd be looking like this. But you know, eventually that graph, while it will jump around at first, you know, it will not have the power to do much jumping as we get out here toward a large number of tosses. And you can think about that easy enough. Suppose that we've got 600 out of 1,000 times it fell that way. Well, then this ratio is 0.6, right? But what's going to happen on the next toss? The next toss is going to give me 601 out of 1,001, or 6,000 out of 1,001, depending upon whether the next toss is a point up or a point down. But there's not much difference between these. You can get your calculator out and look at it. They're about the same. That tells me that this line is going to settle down. What it settles down to is the probability that my thumbtack, since we're talking about point up, is what is the event we're looking at. It's the probability my thumbtack lands head up. So if if we find the probability that the thumbtack lands point up. I'm not saying we do, but if we did, if we found that probability was 0.61, there's only one other thing that can happen. That tack would be point down, would be the only other way that this experiment could resolve itself, like that, point down. Then that probability would have to be 1 minus 0.61, or 0.49. And this is called the law of complements. The probability that something happens is always 1 minus, I'm going to say that again, the probability of an event and its complement. What happens if this doesn't happen? That's the complement. This is what happens if this doesn't happen. These two are always related by P of A, and 1 minus P of A is the probability of the complement. So we'll hit that again too later, but that's the law of complements. There are some things that always happen no matter how you define probability, and they're things like probability of any event A is always greater than or equal to 0. Probabilities are always non-negative numbers, non-negative fractions. Also, the probability of any event A is always less than or equal to 1. So this tells me that anytime I'm working probability problems, the probability of any event is always between 0 and 1. And if I work a probability problem and if I get 2.3 for an answer, I know that answer is wrong, because probabilities always have to be between 0 and 1. They can never be negative. They can never be larger than 1. Okay. The third, I think I told you. If I didn't, you'll see in your book. There's a third way that probability is defined, though we're not going to do anything with it, but that's subjective probability. I say we're not going to do anything with it, but some of the problems that are at the end of this chapter that are assigned have you exercising some subjective probability, but that's pretty much going to be the end of it. And subjective probability would be not just guessing, it's guessing with an expert background. So if we do things like, what's the probability that the Cubs will win 2021 World Series? If you ask me to give you an answer here, and I said, well, that's equal to 0.09, means I'm giving the Cubs a 9% probability of winning. But what's that based on? That's not based on classical probability or empirical probability, relative frequencies. That's just based upon my opinion of the strength of the Cubs team compared to other teams in the league, whether they play good in the heat and how hot I think the summer is going to be, and lots of little factors like that. But it's not classical probability and it's not empirical probability. It's based upon my good judgment, and we will call that kind of probability subjective probability. And since I can't really quantify or tell you how people arrive at subjective probability, it's just not a suitable thing for inclusion in an elementary statistics course. And so we're kind of going to let subjective probability go after the problems at the end of this chapter. Now let's work with what we know so far. Let's work with some other problems and see if we can develop some vocabulary and technique. And so these are problems from page, at least from the exercise set that starts on page 144. And things like this. This is problem number 6. Names of 4 U.S. presidents. Now, if you read in your textbook, it'll give you the names of 4 actual presidents, but why don't we just call them A, B, C, D? One of these was the 14th president. Which one? If you just answer by guessing, the probability that your guess is correct is equal to, now if you're just guessing, then each outcome has a probability of 1 out of 4 of being correct. And they would all be equally likely. They'd each have a probability of 1/4 of being correct. That is, I would have a probability 1 out of 4 of being correct if I'm just guessing. Now, if I know my history, then the probability wouldn't be 1 out of 4, but we're assuming here that I'm using a guess to answer the question, then the probability I'm correct would be 1 out of 4. What if you're taking a multiple choice exam? And for each question, there are 5 possible answers, only one of which is correct. What's the probability that I get a question? Let's see, that looks like a G. I think Q is how you spell question. What's the probability that I get a question correct? Well, there would be 5 possible responses to this multiple choice question, A, B, C, D, E, but 1 out of the 5 would be correct. And so the probability that I get a question correct by guessing would be 0.20, or 1/5, and either would be a correct answer. Now, I want to work a couple more problems for you, but I'm out of working space here, so we're going to have to clear this, and then let's scroll back up to the top and start over again. So let's look at problem 7. Problem 8. And problem 8 says we're going to roll a die. A die would be singular, or half of a pair of dice. And you know that a die is a cube, and so it's got 6 faces, and the number of spots or pips on the faces are 1, 2, 3, 4, 5, 6. The question is, what's the probability that we roll a 6? I said that wrong. What's the probability that we roll a 7 was the question in problem 8. And that's equal to the number of possible outcomes. Well, when I roll a die, I could get the 1, the 2, the 3, and so forth. There are 6 possible outcomes, but exactly 0 of them correspond to rolling a 7. The most I could get would be a 6. And so 0 over 6, or just 0, would be the probability that I roll a 7. Now, any event that has a probability 0 is called in statistics an impossible event. So there would be, lots of possible impossible events. But our first example would be rolling a 7. What if we said, what's x, let's let x equal the number of spots on top. And then let's ask the question, what's the probability when I roll that die that X is less than 9? Well, I think again we can use the classical definition. When I roll the die, there are only 6 outcomes. Now, how many of those outcomes correspond to the number of spots on top being less than 9? There are 6 outcomes. They would be I rolled a 1, I rolled a 2, I rolled a 3, through I rolled a 6. How many of them correspond to X less than 9? Well, all of them do. And so the probability of this event would be 1, and that's as big as probabilities can get. And we call that a sure event. And the description of the sure event can be many, many different things. You know, if we pick a person at random, what's the probability of that person's age is less than 150? Well, that probability is 1, because no person has an age that is 150 or greater. People just don't live that long. And so that would be another example of a sure event. And I mention these just because I want you to get the language. The language is covered, you'll see whenever you read your textbook. But it's up to us to kind of practice the language as well. Problem 10 says, let's get a set of 400 birth records. And the birth records would have lots of useful information on them. They would have the date of birth, and they would have the gender of the child, and they would have the length and the weight of the child. But let's ask questions like, let's let X equal the number of females in the set of 400. And then I'm going to ask you, what's the probability that X is less than or equal to 197? So we've got this random set of 400 births. They weren't selected for any reason. We did a lottery kind of thing and got random births. What's the probability that in this set of 400 we've got 197 or less female births? Is this likely or unlikely? Would that surprise you if this set of 400 had less than or equal to 197 births? I'm going to let you do a subjective probability here, and you just kind of write down on the palm of your hand what you think that number would be. And then I'm going to tell you, and there's no sense holding this off, that this probability is 0.4013. Now, you'll find out very soon how I computed that probability, but this is the second question. The first question was use subjective probability to estimate that. How close were you to 4013? The second question is, do you think that this is a likely outcome? Do you think it's likely that you're going to get 197 births or less? Well, the probability of this happening is 0.4013. Call it 0.4, if you will. And that means that this is going to happen. I'm interpreting this as a relative frequency. This is going to happen about 4 times out of 100. So 4 times out of 100, is that likely or unlikely? I would say that's pretty likely. And I mentioned this a few minutes ago, but I'm going to mention it again. Events with probability less than 0.05, I consider, and so do other statisticians, unlikely. So if the probability of this outcome is 0.4, that's a lot bigger than 0.05. And so I would encourage you to consider that to be a likely outcome. What about the probability that X, again, the number of female births, is greater than or equal to 222 in this set of 400 that we randomly selected? Do you consider that likely or unlikely? First of all, get a number. So use subjective probability and get a number. I'm going to give you a second to think about what that number is. Write it on the palm of your hand. And then compare it with the actual probability, which is 0.157. How close were you? Well, I hope you were respectively close. Would you call this a likely outcome? To get 222 or more female births out of these 400, is that a likely outcome? And the answer is no, because probability of this outcome is less than 0.05. And so we'd say, no, this is a pretty small probability. It's not likely that that's going to happen. How often would this happen? Well, you could expect this to happen about 2 times out of 100. So if you would go get 400 randomly selected birth records, if you would do that 100 times, get 400 birth records 100 times, in 2 of those cases, in 2 of your 100 cases, you would have 222 or more female births. That doesn't happen very often, does it? That's an unlikely event. Let me, because of time, drop down to table 4.1, which is on page 133 of your textbook. And this is a table that shows the result of giving a drug test in a place of business. And the table, I'm going to reproduce it because I want us to be able to refer to it, and we don't all have our books open. So let's look at test results, which are you tested positive for the drug or you tested negative for the drug. And then on the left-hand margin, let's suppose that you are, these are the actual, I don't know if I can write sideways here. Not too bad. Actually, you're a user or not a drug user. So suppose we gave this test to 1,000 employees, and we found that 44 of the 1,000 employees were actual drug users, and they tested positive. The test results came back positive. That is, you are a drug user. And let's just fill in the rest of these numbers without too much comment, just to speed things up a little bit. 860 here. Now, when I fill in what's over here on the sides, these are called the marginal totals. And so I would just add 90 and 144, and I would get 134, and that would be a marginal total for the first column, and that number would tell me out of my 1,000 tests, how many gave a positive test result? And 866 I'd get by adding these two numbers. How many out of my 1,000 tests came back negative for using whatever drug we're talking about here? And then if I do the row totals, these would be called column totals. If I do the row totals, I would get 50, and 50 would be the number of users that were in my sample of 1,000. And then when I would add 860 and 90, I would get 950, and that would be the number of non-users in my 1,000 employees. And mainly what I want to have you think about today is this is a typical situation, and we've done a lot of tests like these recently, not for recreational drugs, but for the presence of either COVID virus DNA or for antigens that are formed if you've been exposed to the DNA. But we still talk about actual has been exposed and has antibodies or not, and test results that are positive or negative. And I'm sure you're very, very familiar, probably more familiar with that than I am. But here, what are these outcomes in this table? Well, if you are a drug user and your test comes back positive, we would call that a true positive, and I'm just going to abbreviate that TP because I don't have much room to write there. And if your test came back positive, but you were not a user, we would call that a false positive. If your test came back negative, but you actually are a drug user, then that would be a false negative. And if you're not a drug user and your test results came back negative, that would be a true negative. So there are like 4 things that can happen whenever you take this drug test. You can be classified as a true positive, true negative, false positive, or false negative. And just to pick an example, problem 22, out of our textbook again, problem 22 says, what's the probability of false positive? What's the probability of a false positive? Well, how many times did we get false positives? We got 90 false positives out of 1,000 tests, and so our relative frequency would be 90 false positives out of 1,000 tests, and this would be empirical probability. And I could leave it that way, or I could say 9 over 100, or I could say 0.09 is the probability of a false positive. It's probably worthwhile thinking about the consequence of that too, because sometimes by the choice of the right test, we can control how many false positives or false negatives we get. A false positive, what are the consequences? You take this drug test and you're a straight Joe or Jane, you do not use drugs, but your test results come back positive for the use of this drug. Well, I mean, that's probably going to mean that you don't get the job. Of course, if you know you didn't use drugs, you could maybe demand a second test and hope for the best here. But a false positive, it's not a good thing. Problem 24. Problem 24. If I just pick one of the 1,000 employees, what's the probability that I pick a non-drug user. Well, how many non-drug users are there? Not a user. The margin tells me there were 950 non-drug users out of 1,000. That's empirical probability again. And this would be 0.95. So 95 times out of 100, if I just select a person at random, that person is going to be a non-drug user. Now, a contrasting question might be, if I just look at a person picked at random, what's the probability that this person is going to get a negative test result? Well, how many people get negative test results? Negative test results, 866 out of 1,000 get negative test results. So the probability that I pick at random a person and that person has a negative test result is 0.866, even though 95% of the people do not use drugs. If the test was perfect, the answer to both these questions would be the same. But you see, these tests are not perfect, and they're never perfect. So if there's something we can do to control the probability of a false positive or a false negative, we need to decide which of these is the most consequential and then control for the one that's most consequential. Unfortunately, we're not going to be able to simultaneously minimize both of these, both the false positive and the false negative. I think this is where we're going to leave the introductory material on probability. You are just absolutely going to have to read the textbook and work problems here, and I'll be working problems with you and available for answering your questions. But this is important material. We're going to be using it for the rest of the semester, and you need to develop the vocabulary and the notions of 5 or 6 different things that we do in probability, and then you'll use those for the rest of the semester. So have a good day, good afternoon, good evening, depending upon when you're watching this, and stay safe. And thank you for being here.